This problem gives us a graph and asks us to find the average rate of change in U, which is the vertical axis utility pleasure units, as the x-axis changes, which we have labeled as the number of units of a product. So this graph is displaying the amount of pleasure or utility that a consumer derives as they consume more and more units of a particular product. So you can see as the number of units of product increases that the utility is increasing. However, the rate of increase appears like it's slowing down. And that's essentially what this problem is meant to point to. So if you look at the average rate of change from a geometrical perspective, you can just think of this as slope. This is saying what's the change in the output, or the y, right? So the change in the y-axis being the utility or pleasure units, per the change in the x-axis, which is the number of units produced. So rise over run, change in y over change in x, slope. We're looking to find the slope across all four intervals here. So if you look at the change in the utility, the y-axis, across the x values of 0 to 1, you can see it changed by 62 units. So we've got 62 pleasure units U per unit of this particular product, which they're just calling X. From 1 unit to 2 units consumed, we've got a change of, let's see, it goes from 62 to 98, which I believe is, what's that? Should be 36, I believe. Change of 36 in the U, utility, pleasure units, per, again, single change in the x-axis because we went from 1 to 2. So this is the amount of utility that the consumer derived from consuming that second product, having already consumed the first. So from 2 to 3, same deal. We're going from 98 to 124. That should be 26. 26 pleasure units per product consumed. And then from 3 to 4, looks like 20. 20 utility pleasure units per unit of this product. So average rate of change, same thing as slope. The context here being this tells us the change in the pleasure units per unit of this product consumed. And you can see that as we go from 0 to 1, 1 to 2, 2 to 3, 3 to 4, that's it's always positive, so it's always going up. So when we look at the second part here, why do the average rates of change decrease as x increases? Well, u itself is increasing, right? The slope's always positive. So any option where it says u is decreasing is out. Looks like I may have double copied one of the same responses here. It's okay. The one that we want to select as our answer is that u is increasing, right? The y-axis is increasing, slope's always positive, but the change in u as we consume more and more products is decreasing. We saw a change of 62 down to 36, down to 26, down to 20. So that should be our answer for part B. This next question here wants us to evaluate the simplified form of the difference quotient for look like a fixed value of x, right? X is always 3, but h is changing to, looks like it's approaching 0. So the way the difference quotient works, or I suppose what it is just an alternate way of defining slope. So you may be used to seeing slope as the change in y divided by the change in x. So this is the same idea. The difference is that instead of having x and another x, they've got this variable h. And h is just the amount of change that we observe in x. So if we start off at x, if we add h to it, we get to the next x. So I can grab the ordered pairs for these 2 points. This first point here has an input x, and since the input is x, the output is just f of x. And the other point over here, right, we've added h to our initial x, so our next x is x plus whatever that h is, and then the associated output with that is the function evaluated at that input x plus h. So there's our ordered pair. And if we find slope with these 2 points, so if I was to subtract my y here from the initial y, f of x, there's my change in the y-axis. And if I grab the x associated with this f of x plus h, and I subtract the x for the other point, we end up with the difference quotient because the x's will cancel out. So we'll go ahead and find that, and then we can evaluate it. And effectively what it does is it just defines the slope for us as a single variable h, so that if we fix our input x at, in this case, 3, we can let the change that we see in x shrink down. In this case, it goes from 2 down to 0.01, and then we look at derivatives later in the chapter. We'll just let h get infinitely close to 0 when we get an instantaneous rate of change or instantaneous slope. So the way to do this is for f of x plus h, which is part of our difference quotient here, in place of x, we're just going to write x plus h. So instead of x squared, it's x plus h squared. So that takes care of f of x plus h. Now we want to subtract f of x, which is defined just simply as x squared. So it was given. And it's over h. Now this might honestly be okay to actually evaluate that table. However, we should simplify this difference quotient. And a good indication that you've got it simplified is that you've got all factors of h in the denominator's place canceled out or removed. So a factor is something that multiplies. If you notice we've got just a single h down in the denominator's place, that being there would be an indication that we would need to simplify. So we're going to expand this term here. We got two binomial factors, x plus h. So we can write them side by side and FOIL them. Or perhaps you're familiar with the form for squaring a binomial. So that's just x plus h times x plus h. And then we got that minus x squared here, all over h. If you notice, we've got a couple things that'll cancel, or at least the x squareds will cancel. And now there's a common factor of h up top. We've got h in both terms, so if we were to pull it out, we got 2x in the first term. We got a single h left in this term since we pulled one of those factors out. And now we can see that as a factor of 1, those h's are canceled. So our simplified difference quotient then is 2x plus h. And as far as filling out this table is concerned, x is always 3. So we could even just go ahead and plug in the 3. 2 times 3 being 6. And now all we got to do to get this table filled out is let h assume all 4 values given here. So for example, if h is 2, we're talking about 8 here. If h is 1, 6 plus 1 would be 7. If we add 0.1 to our 6, we got 6.1, and then we got 0.01 being added. So there's the 4 values in that table. Okay, next up, same idea. We're going to find the simplified difference quotient again, and then we'll fill out a similar table to the previous problem. So this one just has, it's basically the same idea, just has 2 terms. The last one was x squared. This is 5x squared minus x. So we'll start by finding the first term in the numerator of our difference quotient, which is f of x plus h. So again, the way to find that is everywhere you see x in your function, so it's in 2 places, right? It's being squared, and then we're subtracting here. We got to plug in our x plus h. So x plus h goes in there, and x plus h here. So there's f of x plus h. And now we want to subtract f of x. Now because f of x is 2 terms, we want to be careful here and make sure that we subtract the whole thing. So we'll put parentheses. But other than that, f of x is already given to us. So it's 5x squared minus x. And for the difference quotient here, we'll divide everything by h. And this is our difference quotient. We've got, oops, there we go, looks better. We've got f of x plus h right here. Here's f of x plus h minus, here's f of x, and of course there's the h. So now we'll simplify. And we've got this binomial x plus h squared. We'll take care of that by expanding. So we'll multiply x plus h times itself. And then we got a 5 in front. I'll just leave the 5 out in parentheses for now. Then we're going to subtract this x plus h. So we've got a minus x. This negative distributes to the h as well. So there's the second term taken care of here. And then this last term would just distribute the negative. So negative 5x squared plus x all over h. And we want to simplify this. To ensure we've got it simplified, we want to make sure there's no factors of h in the denominator. And currently we've got this h down below. So if we look to combine like terms in the numerator, If we were to distribute this 5, we'll notice this term is going to be 5x squared, so that cancels with this negative 5x squared here. We're going to have 5 times 2 gives us 10xh. We're going to have a plus 5h squared. Again, that's distributing the 5. Then we've got a minus x, but there's also a plus x over here, so that cancels. And then there's this minus h. And now we have 3 terms in the numerator, all of which have a factor of h. So we can pull out that factor of h. We got 10x left in the first term. Second term is just a 5 and an h, since we pulled out one of those factors here. And then we pulled this h out, so there's just left a minus 1. And now as a factor of 1, we can cancel out those h's, and we've got our simplified difference quotient in 10x plus 5h minus 1, like that. And now we can evaluate our table. So like the previous problem, x is fixed at 4. So we can just go ahead and take care of that 10x, call it 40, since x is going to be 4 for all values here. So 10 times 4 is 40. We can even subtract the 1, which is going to give us 39. And now we're left with just adding 5 times whatever h is. So for the first row here, we've got 39, and then 5 times 2 is 10, so 49. We've got h is 1, so 39 plus 5 would give us, 39 plus 5 is 44. Then we've got 0.1, so we do 0.1 times 5 gives us 39.5, and then for the last one, we've got 39.05. And that's that table filled out. Hopefully you found this video helpful. Thank you. Take care. Bye.